Today we are wrapping up the chapter with 6.6, use of proportionality theorems. So, starting off here, we have triangle proportionality theorem, where if in this specific looking triangle, right, where you have kind of like a mid-segment looking piece, except for instead of being a mid-segment, it's parallel to the base, right? QRS and TRU are going to be similar triangles, and then we can make this statement here that RT to TQ is similar to RU to US. So W to X is similar to Y to Z, right? Proportional. And the other way is flip them, right? If both sides are proportional, then triangle, some are parallel. And again, these are pretty simple for proof because parallel lines, parallel angles, you already got angle right there with corresponding, and vice versa. Over here, if they're proportional, and then we have that angle, it's side, and ready to go. Okay? But, however, for those scared about proofs, now that I mentioned that, this lesson is mostly proof-free. Solve for QR. So generally, I'll call it QR, or just kind of give it a variable. We have the parallel, so x to 9 equals 4 to 6. And again, this is 2/3. And then you just find a rule times 3 times 3. So x is 6, or again, cross multiply, right? And you would still get the same answer, which is QR is 6. Okay. Next, determine if it's parallel, same story. 90 over 50, does that equal 72 over 40? Cross multiply, does it work? 3600 equals 3600. Yes. PS parallel QR. And that cross multiply is a quick way to do it. Sometimes you'll be able to tell, 6 over 3 is 2 over 1, right? Real simple one. Moving on, we have multiple parallel lines that it's going to intersect the transversals proportionally, right? So we've got 3 here. So these sides are going to be proportional to these sides, right? So x to y equals t to x. Okay. Next, if a ray bisects the angle, then it is also breaking sides proportionally, right? So these angles are congruent. Again, there's a couple different ways I've seen it set up. This one likes to talk about, we'll call it W. These being WX, Y to Z, right? W to X equals Y to Z. When I learned this, I learned Y to W equals Z to X, right? Like this side to that, similar to this side to that. And it's pretty easy to see where you could get that. Really, we're just flipping these two to get the same idea. So if my original setup looks a little more like the second one, that's why we can kind of mix and match with that proportion to make it work. So again, same story, find the length of YZ. 44 to 35 equals 36 to X. Just a little look at this tells me it's probably not going to be a nice number. So cross multiplying this time, 44x is 35 times 36. Divide by 44. And then plugging into my calculator with the fraction button. Right, we got 35 times 36, ABC 44. And I get 28 and 7/11. Or for those who like the mixed fraction, it would have been 315/11. Right, so using the fraction button, I don't get decimals, but that's how it works. Over here, I like how this bottom one works because it's more of how can you be creative in solving. We've got 7 and 13 angle bisector, and then we know this whole kind of long side of the triangle is 15, and then we're looking just for x over here. This segment is 15 minus x then. So now I can do the same proportion. 7 to 15 minus x equals 13 to x. And we can cross multiply and divide to solve. 7x equals 13 times 15 minus x. So we just have that calculator, 150 plus another 45 is going to be 195 minus 13x. And 7x, move the 13x over, giving me 20x is 195. And divide by 20, giving me 9 and 15/20, or 9.75, 9 and 3/4. Any of those three are the kind of general idea. probably the simplified ones. Those equal x. As I said, a lot more algebraic. And the questions go fairly quickly. In the diagram, 1, 2, and 3 are congruent. Again, what does that give us? Corresponding, corresponding, corresponding. So these are all parallel, right? They basically try to turn into a little bit of a problem. But they say, find the distance between Main Street and South Main Street. Who is naming these streets? Basically, they're saying, what's the difference between F and H and F? Do your proportion with the x, right? Because this is the parallel part. So 150 to 300 equals 120 to x. Real easy math here because this is literally equal to half. So times 120 is our rule, and I get x is 240. However, x is not our answer, right? Our answer is 240 plus that 120, giving me 360. And again, what are we looking at? Distance is yards. So 360 yards is HF. Same idea with this one. Go ahead, try it out. Okay, 96 divided by 15 gives me what, 19.2? And then on the bottom one, 4 to 4.2, right? We got 4 root 2 to 4 equals x to 4. Right? The bottom's the same, so the top's the same. A little bit of 45, 45, 90 triangle hint right there. Okay. You can also cross multiply and divide, so just a little note on that one because you probably haven't done multiplying with these for a while. But basically the outside multiply and the inside multiply. So when I'm dividing by a 4, it divides this outer piece, not the inside. So that's, again, just a little note if you haven't done dividing with roots in a little while, a reminder there. So on this next problem, it says show that the GEC triangle is isosceles, and it is not drawn to scale. So use our parallel. We got parallel here. These two angles are alternate interior. Then using my parallel again, this line, these two angles are corresponding. So it doesn't look great, but it's really like this, where we have these two angles congruent, giving us these sides congruent, and therefore triangle GEC is isosceles. It is OS. Got to mess around with those parallel lines and the angles. Okay. Next one, different question, same diagram. Show that those sides are similar, proportional. Now, if you look at this for a good 10 seconds, you'll see things similar to what we learned. Right? They're talking about these two sides proportional to these two sides. Okay. Now, we've got the angle bisector idea going on. So we technically have W to X equals Z to Y. And let's label what we have here. X to Y equals W to Z. Right? So can we manufacture that from the bisector one? Right? Cross multiply, WY equals XZ. I want X over Y, so divide by Y on both sides, giving me W equals XZ over Y. And now I need the Z on the bottom over here. So dividing by Z on both sides gets me W over Z equals X over Y. Or more particularly, basically just use that formula. EA over EC equals AB over BC. AC, no BC. One last question on this, or sorry, one last question involving this picture. If DEB is a right angle, EB is 3, ED is 8, what is BD? They're going for the most times we can mention a theorem without telling you the theorem. Right here we got EB, DEB is a right angle. So let's say if this is a right angle, ED is 8, EB is 3, what's this segment? They're basically giving you a right triangle, 3, 8. What's the hypotenuse? C squared is 3 squared plus 8 squared. Yep, it's Pythagorean for the 15th time, and I haven't taught you the theorem yet. 9 plus 81 is 64. 8 is 73, so C is the square root of 73. That wraps up that one. Last one, the plan to prove. Given we have some parallel lines, prove the original theorem first one. So plan to prove. I said earlier, this one's a really easy one to prove, right? Technically, what you would do is we have parallel angles in the corresponding form. So corresponding angles congruent, right? We'd have Q congruent to RTU, S congruent to RUT. So that would give us triangle similar, right? Triangle QRS similar to triangle true. Okay. Then what, right? So then you would basically run into this issue where you have X to Y similar to we'll go other letters, W to Z, right? And it's basically a segment addition postulate, right? Because you have TR to QT plus TR, right? If you segment addition postulate equals SU over SU plus UR. And there's a way where you can basically simplify these that repeat out of it to get QT over TR equals SU over UR. I'm not going to show that simplifying process, but you can do that. Again, technically, using our rules from, I believe, 6.2, you can flip them. QT plus TR over TR equals SU plus UR over SU. And then you can basically subtract 1 from both sides to get rid of the SU and TR. And then you can just flip it back. And then flip it again. Or did I write it flipped? Yeah. Yeah, I wrote it flipped. Yeah, these should have been flipped in the first place. So never mind about that flip. It would have just been ready to go right after that. And then you can just subtract 1 from both sides to get here. So I was doing something fancy instead. It was ready for you. And that wraps up today's lesson. If you have questions, as always, email